over a statics physics problem with y'all. Here's Nathan with the first step of problem solving.
Okay, so this is Nathan, and I will be defining our problem as step 1 of our process. So, in our problem, an 80 kilogram mass is hung from 2 cords in a plane. We are given the right side angle is 30 degrees. We are also given that there is a 3, 4, 5 triangle within the larger triangle we'll call AKB. So, looking at the work we have over here, we can see that AB is a transverse line through this triangle we'll call EGF. This means that the angles alpha and omega are actually the same. Thus, if we can solve for omega, we'll have found alpha, the angle we need to solve the problem. So, using the tangent function, we see that the tangent of omega is equal to y over x. Naturally, by reversing and using the inverse tangent function, we see that the inverse tangent of y over x is equal to omega, which is equal to alpha. Thus, alpha is equal to the inverse tangent of y over x. This defines our problem and the information given. Now McKenna will show us how we can solve it.
Hi everyone, this is McKenna with step 3 of the problem solving method, which is generating a solution. So we are generating a solution to the tension problems where we are given 2 wires and a cylinder of mass m. So to solve for the tension in A, B, and BC, we are going to make a free body diagram. So we have the tension in AB pointing up and to the left and the tension of BC up and to the right. And then we have the weight of the object pointing down. So we are going to create a system of equations using this fundamental formula of statics, which is the sum of forces is equal to ma, which is equal to 0 since the object is not moving. So we're going to start in the x plane. So we're going to break our tension into components. So we have TAB of cosine angle 1. So that is because this component is the adjacent side to our reference angle. So we're going to use cosine. And then we have this opposing force on the other side, which is TBC cosine of A2. So we are going to take the tension, this tension component, and subtract this tension component from it. And we're going to equal that to 0 because it's static. Okay, and now we're going to use algebra to isolate our TAB, and we will use this equation later to solve for our TBC. Okay, so now we're going to work in the y-plane. So we have 2 tension components in the y-plane, both pointing up, so we are going to add these. And notice we use sine because it is the opposite of our reference angle. So we have TAB sine of A1 plus TBC sine of A2 minus mg. So we take the weight of the object, which is pointing down, opposite of our tensions, to subtract from those, and we sum it to 0. So now we're going to take the equation from above, and we're going to substitute it into this TAB in order to solve for TBC. So there's a lot of algebra doing that, but at the end we get TBC is equal to mg divided by cosine of A2, tangent of A1 plus sine of A2. So this is the equation that we plug into Excel to generate our solution. Alright, and then we're going to substitute the value we found for tension in BC into our equation from above, so this one up here. So once we do that, we do some algebra, and we're left with TAB is equal to mg times cosine A of 2 over cosine A of 1, cosine A of 2, tangent A of 1 plus sine of A2. And then we're also going to plug this into our Excel spreadsheet to generate a solution for the tension in AB. Alright, Amber's going to do the next step using these equations.
Hi y'all, this is Amber with the 4th step of problem solving, refine and implement. We will be using Microsoft Excel as our tool to aid in solving our problem, as McKenna mentioned earlier. Here, I have already input the information we are given from the problem into a table. I have also named these cells so I can use them in our equations later on. Rather than saying cell D2, I can say cell M. Excel puts out the answers to our angles in radians, and we need them to be in degrees. So I simply took the radian answer and multiplied it by 180 over pi in order to get the degree answer. This will help us later on whenever we are calculating the final answer. Additionally, in order to get the angle values of alpha 1 and alpha 2, we use this similar triangle right here, as you can see on the line from B to A. We use this and trigonometry to find our angle values. Here are the two equations that McKenna derived earlier in the video using trigonometry and algebra. We will use these to find the tensions in TA and TBC respectively. As you can see here, these equations use cell referencing and cell naming in order to give us the values of the tensions in both sides of the cables. Now over here, these are the final answers to our problems whenever the weight of the cylinder is 80 kilograms. In here, we wanted to see if we could change the value of the mass of the cylinder and how that would affect the newtons of the tension in each cable. Now Ethan will go over this in more detail in his section of the video.
Hey guys, Ethan here. This is the fifth and final step of problem solving, verify and test. Before I begin, I want to point out a key feature of the spreadsheet that can assist in validating accuracy and precision. That is the cut margin. In the event we want to have a smaller data set with regard to the mass of the cylinder, we could change the cut margin to a smaller number. This will give our data a more smaller and precise scope for easy and close comparison. Our cut margin is depicted here in cell D7. At this point, it's time to double check our work and make sure our calculations and methods are correct. We can do this by graphing our data generated by Excel and comparing the results to our handwritten calculations. First, we'll take a look at our graphs. I've already plotted the data generated in our spreadsheet. The graphs depict a linear relationship between the tension of the cables and the mass of the cylinder. We could also graph the relationship between the angle measurement and the tension, but for this step we'll only take a look at the mass. We have a graph for both cable BA and BC. Our data is graphed as a solid line because it is theoretical data that has been calculated. Let's compare the results of our spreadsheet with that of our handwritten calculations. When we take a close look at our graph, we can see that the tension at 80 kilograms is roughly 740 or 750. Over here in our answer table, we have 738.313. That's pretty close to our estimate based upon the graph. Likewise, when we look at graph 2, the tension of BC at 80 kilograms is a little bit less than 700, probably about 780, 790, somewhere in there. And likewise, we can see that we have a pretty close estimate based upon the value given. Let's compare this to our handwritten calculations. Here on the left side, we have our handwritten calculations of BC and BA respectively. 682.02 newtons and 738.31 newtons. That's the exact answer we get in our tables here in the spreadsheet. Our answers are validated by our handwritten calculations, spreadsheet, and table. Now to further test our calculations and the validity of the spreadsheet, we can substitute a sample value for the mass of the cylinder and calculate the tension of lines BA and BC. Let's change the mass of the cylinder to 95 kilograms. Our handwritten calculations of the tensions at 95 kilograms are shown here on the right. As you can see here in cells D11 and D12, we have the same answer as our handwritten calculations. When we look at our graphs, we can estimate roughly the same value at 95 kilograms. Lastly, it's important to review our units and ensure they are correct. Both on our graph and in our table, the tension is in newtons, our mass is in kilograms, and our graphs show the same units as well. We have successfully verified and tested our calculations and our spreadsheet. This concludes the 5 steps of problem solving for this statics physics problem. Statics can be applied in many ways around us. An example similar to the problem we solved is a suspension bridge. We can determine the tension of support cables using methods like the ones we applied today. Statics is applied to structures that are at an equilibrium. With that, we must keep in mind the structural integrity of a body. In order to keep a system at a static equilibrium, we must know the maximums, minimums, and capacities of the body with regard to force, both man-made and natural. With that, we conclude our video. We hope you learned something new about statics. Thank you.